close your eyes for just a moment. Breathe in deeply, hold it, and release. Welcome back, fellow travelers. This is the Midnight Explorer, and tonight we're going somewhere you've never been before. Somewhere so vast, so impossibly ancient, that every human who has ever lived could barely comprehend a fraction of its wonder. Tonight, we're going to explore the universe itself, not with telescopes or equations, though we'll meet those who used them. No. Tonight, we're going to feel what it's like to be utterly small, beautifully insignificant, and yet somehow connected to everything that has ever existed. Pour yourself something warm. Settle into the comfort of wherever you are. Let the weight of your day fall away. Because for the next few hours, we're going to drift through the cosmos together, through the minds of dreamers who looked up and dared to wonder. Are you ready? Then let us begin. Picture this with me. It's 40,000 years ago. You're standing on a grassy plain in what will one day be called Africa. The sun has just set, painting the western sky in shades of amber and rose that have no names yet, because language itself is still young, still forming in the throats of your ancestors. You've spent the day gathering roots, berries that stain your fingers purple. Your tribe, your family, sits around a fire that crackles and spits sparks into the growing darkness. The flames dance, casting shadows that seem alive against the faces of people you love more than words can express, because you don't yet have all those words. And then, as the last light drains from the sky, something happens. The darkness doesn't just fall, it opens. One by one, like the slow lighting of distant fires, points of light emerge. Hundreds of them. Thousands. More than you could ever count, even if you knew how to count past the fingers on your hands. They spread across the black canvas of night like seeds scattered by some invisible, eternal hand. You stare. Your breath catches. What are they? This is the moment, one of countless such moments across countless generations, when human consciousness first collided with the universe's greatest mystery. And in that collision, something profound happened, something that would echo through every century that followed. You see, those early humans didn't just see lights, they saw meaning, they saw patterns. The human mind, that beautiful, pattern-seeking instrument, began connecting those dots the way a child connects dots in a puzzle book. Except this puzzle was written in fire across the sky, and nobody had provided the answer key. Over there, do you see it? Those 7 stars that form a shape like a great bear, or perhaps a plow, or maybe a chariot, depending on which story you grew up hearing. And there, that belt of 3 stars in a row, with the sword hanging below, the hunter who watches over the winter sky. Our ancestors didn't know they were looking at balls of nuclear fusion millions or billions of miles away. They didn't know about light years, or photons, or the speed of light. They knew something else, perhaps more important. They knew those lights made them feel something. Wonder. Mystery, connection. In Mesopotamia, in the Fertile Crescent where rivers named Tigris and Euphrates brought life to desert land, priests climbed to the tops of ziggurats, those stepped temples reaching toward heaven, and they watched. Night after night after night, they watched. They noticed that some lights moved, while others stayed fixed. They noticed that the movements followed patterns, cycles, rhythms as reliable as the seasons. These wandering stars, planets, though they didn't call them that yet, became gods. Venus, the morning and evening star, blazing brighter than anything else in the sky. Mars, blood red and ominous. Jupiter, steady and kingly in its slow procession through the constellations. The priests wrote down what they saw on clay tablets, pressing wedge-shaped marks into soft clay that hardened into permanent records. They predicted eclipses. They created calendars. They turned the chaos of the night sky into something ordered, something understandable, something almost manageable. But here's what moves me most about these first stargazers. They were wrong about almost everything. They thought the Earth was the center of creation, with the heavens rotating around us like a great crystalline sphere. They thought the stars were holes poked in the fabric of the sky, letting divine light shine through. They thought comets were omens of disaster, meteors were falling stars, and the Milky Way was a river of milk spilled by a goddess. They were wrong. And yet somehow they were also touching something true. Because when a Babylonian priest stood atop his ziggurat 4,000 years ago, watching Venus rise before the dawn, he was doing the exact same thing you do when you look up at the night sky. He was confronting the mystery. He was asking the questions that make us human. Where do we come from? What is our place in all of this? Are we alone? The answers have changed. The mystery remains. And perhaps that's the first great truth about the universe. It doesn't give up its secrets easily. Every answer we've discovered has come wrapped in a dozen new questions, each more profound than the last.
Let me take you somewhere else now. Somewhere warm and sun-drenched and alive with ideas. It's the 6th century before the Common Era, and you're walking through the streets of Miletus, a Greek city on the coast of what we now call Turkey. The air smells of salt water and olive oil, of fish drying in the sun and bread baking in outdoor ovens. People argue in the marketplace about politics and prices and whether Zeus really exists, or if perhaps the old stories are just that, stories. This is a time of revolution, though it's happening quietly, in the minds of a few strange men who ask strange questions. There's a man named Thales who walks these streets. He's older, with a beard gone white, and people think he's a bit odd. He stares at things, at water flowing, at rocks sitting still, at the moon hanging in the daylight sky, and he asks uncomfortable questions. What if, he says to anyone who will listen, what if there's a natural explanation for everything? What if the gods aren't required? This is dangerous thinking. This is the kind of thinking that could get you in trouble. But Thales persists. He looks at the stars and he wonders, what if they're not divine beings at all, but things, physical objects, following natural laws? What if we could understand those laws? His student Anaximander takes this further. He proposes something so bizarre, so ahead of its time that it wouldn't be accepted for 2,000 years. He suggests that the Earth is floating freely in space, held in place not by Atlas or turtles or pillars, but by being equidistant from everything around it. Balance, symmetry, natural law. Can you imagine that moment? Can you feel what it must have been like to think this thought for the first time? To realize that the solid ground beneath your feet is actually floating in an infinite void, held by nothing but invisible forces. It's terrifying. It's exhilarating. It's the moment when human consciousness made a quantum leap forward. But let's move forward a bit, to another Greek thinker whose name you definitely know. Close your eyes and picture him with me. Aristotle. Born in 384 BCE in a small town in northern Greece. He'll grow up to become the tutor of Alexander the Great, but right now, in this moment I want you to see, he's a younger man walking through the grove of trees near Athens, where Plato's academy meets. He's troubled by something. Everyone says the Earth is the center of everything. The sun, the moon, the planets, the stars all revolve around us. It makes sense. It fits with our experience. We don't feel like we're moving after all. When you throw a rock straight up, it comes straight back down to you. If the Earth were spinning, wouldn't the rock land somewhere else? But Aristotle has noticed something. He's watched lunar eclipses, and every single time, the shadow that the Earth casts on the moon is round. Not sometimes round, not mostly round, always perfectly round. And the only shape that casts a round shadow from every angle is a sphere. The Earth is a sphere, a ball, floating in what? He proposes that the heavens are made of crystalline spheres, nested inside each other, each carrying a planet or star, all rotating around the Earth with perfect circular motion. It's beautiful. It's geometric. It's elegant. It's also wrong. But oh, how productively wrong it is. Because here's what Aristotle gave us. He gave us the idea that the universe follows rules. Not the whims of gods, not random chaos, but rules. Understandable, predictable rules, and if we're clever enough, if we observe carefully enough, we can figure out what those rules are. This is the seed of science, planted in Greek soil, waiting centuries to fully bloom. Now let me introduce you to my favorite Greek astronomer. His name is Aristarchus, and most people have never heard of him, which is a tragedy, because this man, this brilliant, audacious man, figured out something so important, so revolutionary, that it wouldn't be accepted for 1,800 years. He lived in the 3rd century BCE on the island of Samos. He was a mathematician and astronomer, someone who loved numbers and geometry and logic. And he did something that seems simple, but is actually incredibly brave. He tried to measure things. He wanted to know how far away is the moon? How far away is the sun? How big are they? Using nothing but geometry and careful observations, he calculated that the sun is about 19 times farther from Earth than the moon is. The real answer is about 400 times farther, but considering he was doing this without telescopes or computers or even good clocks, it's astonishing he got close at all. But here's what blew his mind. If the sun is that much farther away than the moon, but appears to be the same size in the sky, then the sun must be enormous, much, much bigger than Earth. And then Aristarchus thought, why would something so massive orbit around something so small? What if we've got it backwards? What if the Earth orbits the sun? He proposed a heliocentric model, sun at the center, Earth spinning on its axis and orbiting the sun along with all the other planets. He was right. He was absolutely right. And nobody believed him. The idea was too radical. It contradicted common sense. If the Earth is spinning, why don't we fly off? If we're moving through space at tremendous speed, why don't we feel it? Why do the stars look the same year after year instead of shifting as we change position? These were good questions. Aristarchus couldn't answer them with the knowledge available in his time, so his idea was filed away, forgotten, lost for centuries. But the universe doesn't care about our beliefs. It just keeps being what it is, waiting for us to catch up. Let's move through time now, but slowly, gently, feeling the centuries pass beneath us like pages turning in an ancient book. The Roman Empire rises and falls. The great library of Alexandria burns once, twice, 3 times, each time taking with it scrolls containing knowledge that will never be recovered. Greek and Latin texts scatter to the winds, preserved only in copies of copies, transcribed by monks who sometimes don't understand what they're writing. In Europe, for 1,000 years, the night sky becomes quiet. Oh, people still look up. They still see the stars. But the asking of questions, the building of models, the careful measurement and observation, all of this slows to a trickle. The church provides answers. God made everything, placed the earth at the center of creation, arranged the stars for our benefit, and that's all you need to know. It's not that everyone stops thinking. It's that thinking certain thoughts becomes dangerous. But here's something beautiful. While Europe sleeps, other parts of the world wake up. Let me take you to Baghdad in the 9th century. The Abbasid Caliphate is in full flower, and the Caliph Harun al-Rashid, then his son al-Mamun, have established something extraordinary, the House of Wisdom, Beit al-Hikmah. Imagine a building filled with scrolls and books where scholars from across the known world, Muslims, Christians, Jews, Zoroastrians, work together translating Greek and Indian and Persian texts into Arabic. They're not just preserving knowledge, they're advancing it. Al-Khwarizmi develops algebra here. The word algebra comes from the Arabic al-Jabbar, from his title of his book. Ibn al-Haytham figures out how light and vision work, laying the groundwork for modern optics. Al-Biruni calculates the circumference of the Earth to within a few dozen miles of the correct value. And the astronomers, they build observatories. They create instruments of brass and wood and glass that can measure the positions of stars with incredible precision. They name stars: Aldebaran, Regal, Betelgeuse, Vega, Altair. Even today when we look up, we're often speaking Arabic without knowing it. They preserve the Greek texts that Europe has forgotten. They translate Ptolemy's Almagest, that massive work attempting to explain the motions of heavenly bodies. They don't just copy it, they argue with it, improve it, correct its errors. Al-Sufi creates his Book of Fixed Stars, carefully recording the positions and brightness of over 1,000 stars. He's the first to observe the Andromeda Galaxy, though he doesn't know what it is. He describes it as a little cloud in the constellation of Andromeda. That little cloud is a galaxy containing roughly 1 trillion stars, 2.5 million light-years away, but he's seen it with his naked eye, noted it down, wondered about it. Meanwhile, in China, astronomers are keeping meticulous records. They've been doing this for thousands of years, documenting comets and meteor showers and guest stars, supernovae, with such precision that modern astronomers still use their records to study celestial events from the distant past. In 1006 CE, Chinese and Arab.
Now we come to a moment that changed everything, a pivot point in human history. A moment when the universe began to expand, not physically, not yet in our understanding, but in human consciousness. It's 1543. A man lies dying in a town called Frombork on the Baltic coast of what we now call Poland. His name is Nicholas Copernicus, and he's a canon of the cathedral, a church official, which seems ironic given what he's about to do. In his hands, or perhaps on a table beside his deathbed, lies a book, De Revolutionibus Orbium Celestium, on the revolutions of the heavenly spheres. He's been working on it for decades, hesitant to publish because he knows how controversial its ideas will be. The book proposes something that Aristarchus had suggested 1,800 years earlier. What if the sun, not the earth, is at the center? What if we're not special? What if we're just another planet, spinning and orbiting like all the rest? According to legend, Copernicus receives the first printed copy of his book on the day he dies. He suffered a stroke, is barely conscious, but someone places the book in his hands and perhaps, he understands that his life's work has been preserved, even if he won't live to see its impact. He doesn't. He dies that same day, which is perhaps fortunate because the storm his book creates will rage for over a century. But let's not focus on the controversy. Let's focus on what this meant for humanity's understanding of the universe. Copernicus didn't just move the Earth from the center and put the sun there instead. He did something more profound. He enlarged the universe. You see, If the Earth is spinning and orbiting the Sun, then the stars must be incredibly far away. So far that our motion around the Sun creates no visible parallax, no shift in their positions. They must be distant suns themselves, each perhaps with their own planets. The universe must be vastly bigger than anyone had imagined. Suddenly, the cozy medieval cosmos, with Earth at the center, the planets nearby, and the stars just beyond, becomes a yawning abyss. We're not at the center of a small human-scaled universe. We're on a spinning rock, orbiting an average star, in a cosmos of unimaginable size. This is terrifying. This is liberating. This is the beginning of modern astronomy. Now, let me introduce you to someone else. His name is Galileo Galilei, and he's about to turn the universe inside out. It's 1609. Galileo is in his mid-40s teaching mathematics at the University of Padua. He's heard about a device being made by Dutch spectacle makers, a tube with lenses that makes distant things appear closer, a spyglass, a telescope. Galileo doesn't just hear about it, he builds one. Then he builds a better one. Then a better one still, each time grinding the lenses more precisely, adjusting the focal length, improving the magnification, and then he does something that nobody has thought to do before. He points it at the sky. Imagine being Galileo in that moment. It's night. You're in your study or perhaps on a rooftop. You've spent hours getting your telescope just right. You lift it to your eye, point it at the moon, and the universe explodes into detail. The moon isn't a perfect sphere, smooth and crystalline as Aristotle said the heavens must be. It's rough. It has mountains. It has valleys. You can see shadows changing as you watch, revealing the texture of the lunar surface. The moon is a world, not a light in the sky. Your hands are shaking. You move the telescope. You point it at Jupiter, one of the wandering stars, and you see... What are those? 4 points of light near Jupiter, almost in a line? You watch for an hour. They don't move. You watch the next night. They've changed position, moved around Jupiter. Moons. Jupiter has moons. 4 moons orbiting Jupiter, just as our moon orbits Earth, which means not everything orbits Earth. Copernicus was right. You point the telescope at Venus. Over the course of months, you watch it go through phases: crescent, half, gibbous, full, just like our moon. This is only possible if Venus is orbiting the Sun, not the Earth. You point the telescope at the Milky Way, that cloudy band across the sky. It dissolves into stars. Thousands of them, tens of thousands, more stars than anyone knew existed, revealed by your telescope. Each one a sun, each one, perhaps, with its own planets. The universe keeps getting bigger. Every observation expands it further. Galileo publishes his findings in a small book called Sidereus Nuncius, the Starry Messenger. It becomes an instant sensation. People everywhere want to see these wonders for themselves. Princes buy telescopes. Scholars debate the implications. The Catholic Church gets nervous. Because here's the thing, these aren't just astronomical discoveries. They're philosophical earthquakes. If the heavens aren't perfect, if Earth isn't the center, if we're just one planet among many, then where do humans fit in God's plan? What does it mean for theology, for our sense of self, for our place in creation? The Church summons Galileo to Rome. They tell him to stop teaching that the Earth moves. He agrees, reluctantly. But in 1632, he publishes another book, Dialogue Concerning the Two Chief World Systems, which makes it very clear that he thinks Copernicus was right. This time, the Church has had enough. They put him on trial. They threaten him with torture. He's 70 years old now, ill, tired. He recants. He says he was wrong to suggest the Earth moves. They sentence him to house arrest for the rest of his life anyway. Legend says that as he leaves the trial, he mutters under his breath, "Et pur si move," and yet it moves. Whether he actually said this or not? Probably not, honestly. It captures something true. The universe doesn't care what we believe about it. It doesn't care about our trials or our theologies or our cherished ideas about our own importance. It just keeps being what it is. The Earth moves. It spins at about 1,000 miles an hour at the equator. It orbits the Sun at about 67,000 miles an hour. The Sun itself is moving, carrying us with it around the center of the Milky Way galaxy at about 514,000 miles an hour. The galaxy itself is moving through space at about 1.3 million miles an hour. We all are moving, all the time, through an immense cosmic dance that we can barely perceive. And Galileo, looking through his telescope, began to glimpse the true scale of that dance.
Let's jump forward a few decades. It's Christmas Day, 1642. In a small manor house in Lincolnshire, England, a baby is born prematurely. So small that his mother later said he could fit in a quart mug. Nobody expects him to survive. His name is Isaac Newton, and he will change how we understand absolutely everything. But let's not jump ahead. Let's watch him grow up. His father dies before he's born. His mother remarries and sends young Isaac to live with his grandmother. He's a lonely child, isolated, strange. He doesn't play well with others. He prefers to build things, little models, water clocks, sundials. He draws. He thinks. In 1661, at age 18, he enrolls at Cambridge University. He's poor, pays his way by working as a servant for wealthier students. But his mind is extraordinary. He devours books on mathematics and philosophy. He teaches himself things that aren't in the curriculum. Then, in 1665, the plague comes to England. Cambridge closes. Newton returns to Lincolnshire, to his mother's farm, and there, in isolation, he has 2 years to just think. These will be perhaps the most productive 2 years in the history of human thought. He invents calculus. Independently, Leibniz will invent it too, leading to a bitter dispute over priority. He conducts experiments with light, discovering that white light is actually composed of all the colors of the rainbow. And he begins thinking about motion, about why things move the way they do, about what makes the planets orbit the sun. The story about the apple is probably exaggerated. You know the one. He's sitting under an apple tree, an apple falls on his head, and suddenly he understands gravity. It's a nice story, but the truth is more interesting. What Newton actually wondered was this. If an apple falls down and the moon is up in the sky, why doesn't the moon fall down too? Or, wait, what if it does? What if the moon is falling all the time, but it's also moving sideways fast enough that it keeps missing the Earth? What if orbiting is just constantly falling, but never hitting? Newton worked out the mathematics. He calculated the force needed to keep the moon in its orbit. He realized it was the same force that makes the apple fall, gravity. The same force, just acting over a much greater distance. This is the moment when the heavens and the earth become united. For thousands of years, philosophers had insisted that the heavens operated by different laws than the earthly realm. The heavens were perfect, eternal, unchanging, governed by different principles. The earth was imperfect, temporary, corruptible. Newton says, no, it's all the same. The same laws that govern an apple falling from a tree govern the motion of the moon, the planets, the stars. Everything in the universe obeys the same rules. He writes this all down in one of the most important books ever published, Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy. We usually just call it the Principia. In it, he lays out 3 laws of motion and the law of universal gravitation.
Every object attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. Simple, elegant, and it explains everything. Why planets orbit in ellipses. Kepler had observed this, but didn't know why. Why tides rise and fall, the moon's gravity pulling on Earth's oceans. Why comets appear and disappear on predictable schedules. They're orbiting the sun too, just on very elongated paths. Why you weigh less on a mountaintop than at sea level. You're farther from Earth's center, so gravity is slightly weaker. The universe, Newton shows, is a clockwork mechanism. Wind it up with the right initial conditions, and you can predict its motion forward and backward in time with perfect precision. This is intoxicating. This is the birth of the age of reason, the Enlightenment, the idea that human intellect can comprehend the cosmos. If Newton could figure out the laws of motion and gravity using nothing but his mind and some mathematics, what else might we figure out? For 200 years, Newton's universe reigns supreme. Physicists and astronomers use his laws to discover new planets. Neptune is found in 1846 because its gravity perturbs Uranus's orbit in ways that Newton's laws predict. Engineers use his principles to build machines, bridges, railroads. The Industrial Revolution, in many ways, is applied Newtonian physics. But Newton himself, despite his achievements, remains humble about the big questions. Late in his life, he writes, "I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore and diverting myself in now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me." The great ocean of truth. What a beautiful phrase. What a perfect encapsulation of the scientific attitude. The recognition that no matter how much we learn, there's always infinitely more that we don't know. And Newton was right, because even as his laws explained so much, there were cracks, tiny anomalies. Mercury's orbit didn't quite match Newton's predictions. Light behaved strangely, sometimes like a particle, sometimes like a wave. And the speed of light, when measured carefully, always came out the same regardless of how fast the observer was moving, which made no sense in a Newtonian universe. These cracks would eventually break open the entire edifice of classical physics. But that comes later. For now, let's sit with Newton's achievement. Let's appreciate what he gave us. A universe that makes sense, that follows rules, that can be understood through careful observation and mathematical reasoning. It's not a mystical universe anymore. It's not governed by the whims of gods. It's a cosmos we can comprehend, at least partially. And that comprehension is perhaps our birthright as curious, pattern-seeking, question-asking humans.
Let me tell you about light. Not metaphorical light, not the light of understanding or enlightenment, but actual physical light. Photons streaming through space, the fastest thing in the universe, the cosmic speed limit, the messenger that brings us all our information about the heavens. For most of human history, people assumed light traveled instantaneously. You see something the moment it happens, right? There's no delay. The sun rises and immediately you see it rising. Lightning flashes, and immediately you see the flash, though the thunder comes later, which is interesting, isn't it? But some philosophers wondered. Empedocles in ancient Greece proposed that light must travel, must take time to get from one place to another. Most people ignored him. It's not until 1676 that anyone proves this. An astronomer named Euler Roemer is studying Jupiter's moons, particularly Io, the innermost large moon. Io orbits Jupiter every 42.5 hours, disappearing behind the planet, then reappearing in an eclipse that can be precisely timed. Roemer notices something strange. The eclipses don't happen when they're predicted. When Earth is farther from Jupiter, the eclipses seem to happen later. When Earth is closer, they happen earlier. The difference is only about 22 minutes over the course of Earth's orbit,
but it's measurable, consistent, and puzzling. Unless light takes time to travel. If light has a finite speed, then when Earth is farther from Jupiter, the light carrying the image of Io's eclipse has to travel farther to reach us, so we see it later. When Earth is closer, we see it sooner. Romer calculates the speed of light, not very accurately, but he gets it within the right order of magnitude. Light travels very, very fast, but not infinitely fast. It takes time to cross even the distance between planets. This discovery changes everything. Because if light takes time to travel, then when we look at distant objects, we're not seeing them as they are now, we're seeing them as they were when the light left them. Look at the sun. You're seeing it as it was about 8 minutes ago. That's how long light takes to travel from the sun to Earth. If the sun suddenly vanished, it won't, but imagine. We wouldn't know for 8 minutes. We'd still see it shining in the sky, still feel its warmth, blissfully unaware that our star had disappeared. Look at the nearest star beyond the sun, Alpha Centauri. You're seeing it as it was about 4 years ago. The light touching your eyes right now left that star before the last presidential election. Look at the Andromeda Galaxy, that little cloud that Al-Sufi observed 1,000 years ago. You're seeing it as it was 2.5 million years ago. When that light began its journey to Earth, humans had just begun to emerge as a distinct species. We were barely out of the trees. We hadn't invented language yet, or tools beyond the most primitive rocks. That light has been traveling through space, through the darkness, for longer than modern humans have existed. Do you see what this means? When we look out into space, we're looking back in time. The universe isn't just vast in distance, it's vast in time. Every observation is an act of archaeology, of peering into the past. This realization doesn't fully sink in until the 20th century, but it begins here with Romer, watching Jupiter's moons and wondering why they don't keep perfect time. Now let me introduce you to another character in our story, William Herschel. Born in Hanover, Germany in 1738, he moves to England as a young man and works as a musician, conducting orchestras, composing symphonies, teaching music lessons. Astronomy is just a hobby. But what a hobby! He becomes obsessed with building telescopes, each one larger and more powerful than the last. He grinds mirrors himself, spending hours bent over a grinding stone, his sister Carolyn helping him, both of them working late into the night to create mirrors that can gather more light, reveal fainter objects, see deeper into space. On March 13, 1781, Herschel is conducting one of his systematic surveys of the sky, methodically examining every visible star, when he notices something odd. One of the stars looks different, slightly fuzzy, disc-like rather than a point. Over the next few nights, he observes that it moves against the background of fixed stars. He's discovered a new planet, the first planet discovered in recorded history. Uranus. Side note, Herschel wanted to name it Georgium Sidus, George's star, after King George III. Thankfully, this didn't stick. Can you imagine? Mercury, Venus, Earth, Mars, Jupiter, Saturn, George. The name Uranus, from the Greek god of the sky, was suggested by astronomer Johann Bode and eventually adopted. This discovery makes Herschel famous. He's given a royal salary and can devote himself full-time to astronomy. He builds even larger telescopes, including one with a mirror 4 feet across, the largest telescope in the world for 50 years. With these instruments, Herschel does something remarkable. He tries to map the shape of the Milky Way. Using statistical methods, counting stars in different directions, estimating their distances, he creates the first rough map of our galaxy. He realizes it's shaped like a disk, a vast collection of stars all orbiting around a common center. But he makes a mistake, an understandable one. He places our solar system near the center of this disk. He assumes that we can see about equally far in all directions, so we must be somewhere in the middle. It will take another century and a half before anyone realizes how wrong this is. But that's the nature of discovery. We're always seeing from where we stand, and it takes enormous effort to realize that where we stand isn't special. Herschel's sister deserves her own moment here. While Herschel is often celebrated, Caroline Herschel is the first woman to discover a comet, the first woman to have her work published by the Royal Society, the first woman to be paid for scientific work in England. She discovers 8 comets in total, catalogs thousands of nebulae, and when her brother builds his massive telescopes, she's there beside him, recording observations, doing calculations, making this work possible. On cold English nights, she stands for hours with her telescope, searching the skies. She's methodical, patient, brilliant, and she's often overlooked in history books, her contributions attributed to her more famous brother. But without her, his work would have been impossible. This pattern repeats throughout the history of astronomy. Behind many famous male astronomers stand women, wives, sisters, daughters, assistants, doing the actual work of observation, calculation, cataloging, computing orbits, measuring stellar positions, classifying spectra, often unpaid, rarely credited, but essential. We'll meet more of them as our story continues, because the universe doesn't care about gender or social status or who gets the credit. It reveals itself to anyone patient enough to look, careful enough to measure, brave enough to question.
Here's a question that haunted astronomers for centuries. How far away are the stars? We could measure distances on Earth easily enough, pace them out, use surveying instruments, triangulate positions. But the stars? They're so far away that all attempts at measurement failed. They showed no parallax, no apparent shift in position when viewed from different locations or at different times of year. This bothered people a lot, because without knowing distances, you can't really understand anything. Is that star dim because it's far away, or dim because it's actually a faint star that happens to be close? Is that star bright because it's close, or because it's genuinely brilliant and just happens to be farther away? The breakthrough comes in 1838. 3 astronomers, working independently, finally succeed in measuring stellar parallax, the apparent shift of a star against more distant background stars as Earth orbits the Sun. Friedrich Wessel, in Germany, measures the parallax of a star called 61 Cygni. Thomas Henderson, in Scotland, measures Alpha Centauri. Friedrich Struve, in Russia, measures Vega. The measurements are tiny, fractions of an arcsecond, like trying to measure the width of a coin from a mile away, but they're real, measurable, repeatable. 61 Cygni is about 11 light-years away. Alpha Centauri is 4.4 light-years away. Vega is 25 light-years away. These are distances that beggar the imagination. A light-year is about 6 trillion miles. Alpha Centauri, our nearest stellar neighbor, is 26 trillion miles away. If you could drive to Alpha Centauri at highway speeds, never stopping, it would take about 50 million years to get there. And that's the closest star. But now we can measure. Now we can begin to build what astronomers call the cosmic distance ladder. A series of methods, each one reaching farther than the last, each one calibrated against the methods that came before. For nearby stars, we use parallax. For more distant stars, we look at their spectra, the pattern of colors in their light, which tells us what kind of star it is, which tells us how intrinsically bright it should be, which lets us calculate its distance by measuring how bright it appears to us. This method, discovered by Henrietta Swan Leavitt in 1908, would change astronomy forever. But I'm getting ahead of myself. Let me take you to Paris in 1814. A man named Joseph von Fraunhofer, a German glassmaker and optician, is doing something curious. He's passing sunlight through a prism to create a rainbow, Nothing new there, Newton did the same thing, but Fraunhofer is looking very closely at that rainbow. And he notices something strange. The rainbow isn't continuous. It has dark lines in it. Hundreds of them, thin dark gaps where specific colors are missing. He has no idea what causes these lines, but he's a careful observer, so he maps them. He catalogs over 500 of these dark lines in the solar spectrum, labeling the most prominent ones with letters A, B, C, and so on. Later, much later, scientists figure out what these lines mean. They're absorption lines, caused by specific elements in the sun's atmosphere absorbing specific wavelengths of light. Each element has its own unique pattern of lines, like a fingerprint. This means you can look at a star's spectrum and know what it's made of. You can analyze the chemical composition of something billions of miles away, something you can never touch, can never visit, can never bring back to a laboratory. Think about how profound this is. For all of human history, the stars were unreachable, unknowable, divine. And now, suddenly, we can dissect their light and know what elements they contain. We can know if a star has hydrogen, helium, carbon, oxygen, iron. We can know its temperature, its pressure, its motion toward or away from us. We can know things about objects so distant that their light takes years or centuries or millennia to reach us. A woman named Cecilia Payne, later Cecilia Payne-Gaposchkin, will use this technique in 1925 to discover what stars are made of. Her doctoral thesis, which her advisor calls the most brilliant PhD thesis ever written in astronomy, demonstrates that stars are primarily composed of hydrogen and helium, not the heavier elements common on Earth. This is controversial at first. Her doctoral thesis advisor, the famous astronomer Henry Norris Russell, convinces her to downplay this conclusion in her published thesis, saying it's probably wrong. 4 years later, he'll realize she was right and will publish the same conclusion himself, often getting credit for the discovery. This is the pattern, again and again, women doing brilliant work, men getting the credit. But the universe doesn't care about our petty human politics. The truth emerges eventually, even if justice doesn't always follow. Now, let me tell you about photography because it changes astronomy completely. For thousands of years, astronomical observation was limited by human vision. You could only see what your eye could see in the moment. You couldn't study faint objects in detail. You couldn't go back and re-examine an observation. Everything depended on careful note-taking, sketches, memory. Then, in the mid-1800s, photography is invented, and astronomers realize, wait, we can photograph the sky. We can point a camera at a star or nebula or galaxy, expose it for minutes or hours, and capture light too faint for the human eye to ever see. We can create permanent records that can be studied for years afterward. The first astronomical photograph of a celestial object, the moon, is taken in 1840. The first photograph of a star, Vega, is captured in 1850. The first photograph of a nebula, the Great Orion Nebula, comes in 1880. And then things accelerate. Observatories start creating photographic surveys of the sky, taking thousands of images, cataloging millions of stars. They hire teams of people to analyze these photographs, measuring stellar positions, estimating brightness, classifying spectra. These teams are mostly women. This might surprise you, but there's a practical reason. Women can be paid less than men. Observatory directors realize they can hire smart, educated women, often recent college graduates, for a fraction of what they'd have to pay men with equivalent qualifications. They call them computers, human computers, whose job is to do calculations and measurements. At Harvard College Observatory, Director Edward Pickering hires dozens of these women. They become known as Pickering's harem, or later more respectfully, as the Harvard Computers. And they do extraordinary work. Annie Jump Cannon develops a classification system for stellar spectra that is still used today. The OBAG-FKM sequence, often remembered by the mnemonic, "Oh, be a fine girl, guy, kiss me." She personally classifies over 350,000 stars, more than anyone else in history. Henrietta Swan Leavitt, studying photographic plates of stars in the Small Magellanic Cloud, discovers the period luminosity relationship for Cepheid variables, the relationship that will allow astronomers to measure cosmic distances and eventually discover that the universe is expanding. Williamina Fleming discovers the Horsehead Nebula, one of the most famous dark nebulae in the sky. She discovers 10 novae, 59 gaseous nebulae, and over 300 variable stars. These women are paid 25 to 50 cents an hour, about $7 to $15 an hour in today's money. They work long hours in windowless rooms hunched over glass photographic plates, measuring and recording. They're not allowed to use the telescopes themselves. Their names don't appear on most of the papers that result from their work. But they're doing science. Real, important, groundbreaking science. And slowly, grudgingly, the astronomical community begins to recognize this. The universe is beginning to reveal itself through photography, through spectroscopy, through careful statistical analysis of thousands and thousands of observations. And the picture that emerges is strange, beautiful, and far larger than anyone imagined.
Let me paint a scene for you. It's 1920. The place is the Smithsonian Museum of Natural History in Washington, D.C. Two astronomers are about to have a debate that will reshape our understanding of the universe. On one side, Harlow Shapley, director of the Harvard College Observatory, brilliant, confident, convinced he understands the true scale of the cosmos. On the other side, Heber Curtis from the Lick Observatory in California, equally brilliant, equally confident, with a completely different vision of the universe. The question they're debating? What are the spiral nebulae? For years, astronomers had observed these curious objects, fuzzy patches of light with a spiral structure, spinning pinwheels in the sky. They'd cataloged them. The most famous, the Andromeda Nebula, was visible to the naked eye as a faint smudge. Telescopes revealed its spiral structure, beautiful and mysterious. But what were they? Shapley argues that they're part of our Milky Way galaxy, clouds of gas and dust, perhaps places where stars are forming. The Milky Way, he says, is enormous, 300,000 light-years across, and contains everything we can see. The entire universe is essentially one galaxy, ours. Curtis argues something more radical. He thinks the spiral nebulae are island universes. Separate galaxies like our own, far outside the Milky Way, each containing billions of stars. The universe, he suggests, is vastly larger than anyone has imagined, filled with countless galaxies scattered through space. The debate is inconclusive. Both men make good arguments, both have evidence, but neither can prove their case definitively. The answer comes 4 years later, from an astronomer named Edwin Hubble. Hubble is working at Mount Wilson Observatory in California, using the 100-inch Hooker telescope, at the time the largest telescope in the world. He's photographing the Andromeda Nebula, taking long exposures, studying its structure. And then, in October 1923, he finds something. A variable star. A Cepheid variable, one of those stars Henrietta Leavitt had studied, whose period of variation tells you its absolute brightness. Hubble measures the period. He calculates the star's actual brightness. He compares this to how bright it appears in his photographs. And he realizes this star is incredibly far away, about 900,000 light-years away. The modern estimate is about 2.5 million light-years, but Hubble's distance scale was off. Even so, his basic conclusion was right. If Andromeda is 900,000 light-years away, and if the Milky Way, as Shapley had argued, is only about 300,000 light-years across, then Andromeda can't be part of the Milky Way. It must be a separate galaxy, an island universe. Curtis was right.
When Hubble's discovery is announced, it fundamentally changes our understanding of the cosmos. The universe isn't one galaxy, it's countless galaxies. Each galaxy contains billions of stars. Each galaxy is separated from other galaxies by vast distances, millions of light years of mostly empty space. Let that sink in for a moment. Before 1924, we thought the universe was essentially one galaxy, big, but contained, knowable. After 1924, we know the universe contains billions of galaxies, each one a vast city of stars, scattered through a space so large we can barely comprehend it. But Hubble isn't done. His next discovery will be even more shocking. He starts measuring the spectra of galaxies, analyzing their light to see what wavelengths are present. And he notices something strange. Almost every galaxy's spectrum is shifted toward the red end of the spectrum. Red-shifted, astronomers call it. This is the Doppler effect. You've experienced it with sound. When an ambulance approaches, its siren sounds higher-pitched, and when it drives away, the pitch drops. The same thing happens with light. If an object is moving away from you, its light gets shifted toward longer, redder wavelengths. If it's moving toward you, its light gets shifted toward shorter, bluer wavelengths. Almost every galaxy Hubble observes is redshifted. They're all moving away from us. Weird, but okay. Maybe we're in a special location, a place that everything else is moving away from. But then, Hubble notices something even stranger. The farther away a galaxy is, the faster it's moving away from us. There's a relationship, a linear relationship between distance and velocity. Double the distance, double the recession speed. This is published in 1929 as Hubble's law, and it changes everything. Because if all galaxies are moving away from each other, with more distant galaxies moving faster, then the universe itself must be expanding. Not expanding into something, just expanding. Space itself is stretching, carrying galaxies along with it like raisins in a rising loaf of bread. If the universe is expanding now, then in the past, it must have been smaller. Go back far enough, and everything, all the matter in all the galaxies, must have been compressed into a smaller and smaller space. Go back to the very beginning? And what? Where did it all come from? We're going to explore that question soon. But first, let me sit with you in the wonder of this discovery. The universe is expanding. Space itself is stretching. Galaxies are rushing away from each other at speeds that increase with distance. The cosmos is dynamic, evolving, changing on timescales of billions of years. This is not the eternal, unchanging universe of Aristotle. This is not even the clockwork universe of Newton, predictable and mechanical but static in its overall structure. This is something new, a universe with a history, a universe that, if we follow the logic backward, must have had a beginning.
Let me take you to Belgium in the 1920s. There's a man here, a Catholic priest named Georges Lemaitre, who was also a physicist and astronomer. He's studying Einstein's equations of general relativity, those beautiful, complex equations that describe gravity not as a force, but as a curvature of space-time itself. Lemaitre is doing something that Einstein himself has been reluctant to do. He's taking the equations seriously in their most radical implications. Einstein's equations suggest that space itself can curve, can warp, can stretch or compress. They describe a dynamic universe, one that changes over time. But this seems wrong to Einstein. The universe should be eternal and static, unchanging.
So Einstein adds a term to his equations. He calls it the cosmological constant, specifically to make the universe static, to prevent it from expanding or contracting. Lemaitre looks at the original equations without this added term and realizes if Hubble's observations are correct, if galaxies really are moving away from each other, then the universe is expanding, just as the original equations predicted. And if the universe is expanding now, then in the past it was smaller. Go back far enough, and the universe must have been incredibly tiny, perhaps even a single point. In 1931, Lemaitre proposes what he calls the hypothesis of the primeval atom, or more poetically, the cosmic egg. The entire universe, he suggests, began as a single quantum, a primeval atom containing all the matter and energy that would become stars, galaxies, planets, everything. This primeval atom was unstable and exploded, and the universe has been expanding ever since. Most scientists think this is ridiculous. The universe has always existed, they insist. It has no beginning. The idea that everything came from nothing, from a single point, is absurd. One astronomer, Fred Hoyle, mockingly calls Lemaitre's idea the Big Bang during a radio broadcast in 1949. He means it as an insult, a way to make the idea sound absurd. The name sticks. But evidence keeps accumulating. The expansion of the universe is real. More and more measurements confirm Hubble's law. If you run the expansion backward in time, everything does converge toward a single point. The math is clear, even if the implications are disturbing. And then, in 1964, two radio astronomers make an accidental discovery that will clinch the case. Arno Penzias and William Holsey are working at Bell Labs in New Jersey using a large horn antenna to detect radio waves bouncing off satellites. But they keep picking up a persistent noise, a hiss of radio static that comes from every direction in the sky, day and night, all year round. It's faint but consistent, and it's driving them crazy because they can't figure out what's causing it. They check everything. They clean the antenna. They even remove some pigeons that had been nesting inside and clean out what they delicately call a white dielectric material. Pigeon droppings. The noise persists. Meanwhile, just down the road at Princeton University, a team of physicists led by Robert Dicke has been working on a theoretical prediction. If the universe really began in a hot, dense state, a Big Bang, then there should be leftover radiation from that initial explosion. The early universe would have been incredibly hot, glowing with intense light. But as the universe expanded and cooled, that light would have been stretched to longer wavelengths, redshifted down into the microwave range of the spectrum. If the Big Bang really happened, there should be a faint glow of microwave radiation filling all of space, coming from every direction, the afterglow of creation itself. Dicke's team is building equipment to search for this radiation when someone mentions the strange noise that Penzias and Wilson can't explain. Dicke realizes immediately what it is. Boys, we've been scooped! Penzias and Wilson have accidentally discovered the cosmic microwave background radiation, the leftover glow from the Big Bang. They've found direct evidence that the universe had a hot, dense beginning 13.8 billion years ago. For this discovery, they'll win the Nobel Prize in 1978. Dicke, who predicted the radiation, won't share it. A reminder that in science, as in life, timing matters, and luck plays a role. But let's think about this. Let's really think about it. The universe had a beginning. Not just the matter in the universe, not just the galaxies or stars, but space and time themselves began at a specific moment about 13.8 billion years ago. Before that moment, there was no before. Time itself didn't exist. Space didn't exist. The question, what came before the Big Bang, doesn't even make sense because before is a time concept, and time began with the Big Bang. In the first fraction of a second after the Big Bang, the universe was unimaginably hot and dense, so hot that atoms couldn't exist, so hot that even atomic nuclei couldn't exist. There was just energy, pure energy, in forms we can barely comprehend. As the universe expanded, it cooled. After a few minutes, it was cool enough for protons and neutrons to stick together, forming the nuclei of the lightest elements: hydrogen, helium, a tiny bit of lithium. After about 380,000 years, it cooled enough for electrons to bind to these nuclei, forming actual atoms. And at that moment, the universe became transparent. Light could suddenly travel freely through space. That light is what Penzias and Wilson detected, light that has been traveling through space for over 13 billion years, stretched by the expansion of the universe from visible light into microwaves. When you see the cosmic microwave background in a map, you're looking at a picture of the universe when it was just 380,000 years old, a baby picture of the cosmos. And here's something beautiful. That light is everywhere. Right now, as you sit wherever you are, you're bathed in ancient photons that have been traveling through space since shortly after the universe began. They're passing through your body, billions of them every second, carrying information about the infant universe. You are literally surrounded by the light of creation. Let that wash over you. You are being touched by the beginning of everything.
Now I need to tell you about something strange. Something that will make you question everything we've discussed so far. In the 1930s, an astronomer named Fritz Zwicky is studying the Coma Cluster, a large group of galaxies bound together by their mutual gravity. He's measuring how fast these galaxies are moving relative to each other, and he's doing some calculations. If you know how massive a cluster is, and you know the laws of gravity, you can predict how fast galaxies in that cluster should be moving. It's just Newton's laws applied on a cosmic scale. Zwicky does the math, and something doesn't add up. The galaxies are moving much too fast. At the speeds he's measuring, they should fly apart. The cluster shouldn't hold together at all. Yet clearly it does hold together. It's been stable for billions of years. The only explanation: there must be much more matter in the cluster than we can see. Some kind of invisible matter, dark matter, Zwicky calls it, that provides additional gravity to hold everything together. Most astronomers ignore him. Zwicky has a reputation for being difficult, for making grand claims. Besides, invisible matter? It sounds too much like adding epicycles to fix a broken theory. Surely there's a simpler explanation. But similar problems keep appearing. In the 1970s, an astronomer named Vera Rubin is studying the rotation curves of spiral galaxies. She's measuring how fast stars orbit around the galactic center at various distances. In a solar system, planets farther from the sun orbit slowly. That's Kepler's laws, confirmed by Newton's gravity. Neptune orbits much more slowly than Earth. This makes sense. The farther you are from the source of gravity, the weaker its pull, so you don't need to orbit as fast to maintain your orbit. The same should be true for galaxies. Stars near the galactic center should orbit quickly. Stars far from the center, out in the edges of the galaxy where there are fewer stars and less matter, should orbit slowly. But that's not what Rubin finds. Stars at the edges of galaxies orbit just as fast as stars near the center. The rotation curves are flat, not dropping off as they should. Again, the only explanation is invisible matter, dark matter, extending far beyond the visible edges of galaxies, providing the extra gravity needed to keep those outer stars moving so fast. Rubin faces skepticism partly because she's a woman in a male-dominated field. She perseveres, collecting data from dozens of galaxies, all showing the same pattern. The evidence becomes overwhelming. We now know that the visible matter in the universe, stars, planets, gas clouds, everything we can see with telescopes, makes up only about 5% of the total matter and energy in the universe. About 27% is dark matter, matter that doesn't emit or absorb light, that we can only detect through its gravitational effects. The remaining 68% is something even stranger, dark energy, a mysterious force causing the expansion of the universe to accelerate. Think about that for a moment. 95% of the universe is invisible to us. We're walking through a cosmos where everything we can see, everything we've ever detected with any instrument, is just a tiny fraction of what actually exists. It's humbling. It's dizzying. It's a reminder that for all our progress, for all our telescopes and equations and theories, we're still fumbling in the dark, trying to understand a universe that is stranger and more mysterious than we ever imagined. What is dark matter? We don't know. Physicists have proposed dozens of candidates, exotic particles with names like WIMPs, weakly interacting massive particles, and axions and sterile neutrinos. Experiments deep underground and in space are searching for these particles. So far, nothing definitive. What is dark energy? We know even less. It might be a property of space itself. Vacuum energy that becomes more dominant as the universe expands. It might be related to Einstein's cosmological constant, that term he added to his equations and later called his biggest blunder. Or it might be something we haven't even imagined yet. The universe, it turns out, is mostly mystery. And that's okay. That's beautiful in its way, because it means there's so much left to discover, so many questions still to answer, so many adventures yet to be had in the realm of ideas. Let me tell you about something that shouldn't exist. Something so strange, so counter to common sense, that even Einstein, whose equations predicted them, refused to believe they were real. Black holes. The story begins with Einstein's general relativity, published in 1915. These equations describe gravity as a curvature of space-time. Mass curves space around it, and objects follow the curvature. That's what we perceive as gravity. Within months of Einstein publishing his equations, a German physicist named Karl Schwarzschild, serving in the German army during World War I, calculating artillery trajectories during the day and working on physics at night, finds an exact solution to Einstein's equations. Schwarzschild's solution describes what happens around a spherical mass, and it contains something disturbing. If you compress enough mass into a small enough volume, space curves so severely that nothing, not even light, can escape. There's a boundary, the Schwarzschild radius, and anything that crosses that boundary is gone forever, fallen into a region from which there is no return. Schwarzschild dies a few months later from an illness contracted on the Russian front. Einstein publishes Schwarzschild's solution, but doesn't think these objects can actually exist in nature. They're mathematical curiosities, he says, not real things. For decades, most physicists agree. Black holes are too weird, too extreme. Surely nature has some mechanism to prevent them from forming. Then, in the 1960s, everything changes. Astronomers start detecting strange objects, quasars, blazars, sources of intense radiation coming from the centers of distant galaxies. The only way to explain the energy output is to invoke black holes. Supermassive black holes, millions or billions times the mass of the Sun,
with gas spiraling into them, heating up to millions of degrees and radiating intensely before crossing the point of no return. A physicist named John Wheeler coins the term black hole in 1967. Before that, they were called frozen stars or collapsed stars, much less catchy names. The name captures the imagination, a hole in space, black because not even light can escape. Now here's where it gets really strange. Let's explore what would happen if you fell into a black hole. Not that you should try this, but it's a fascinating thought experiment. From your perspective, falling in, nothing special happens when you cross the event horizon, the boundary of no return. There's no barrier, no sign, no sensation of crossing. You just fall. Space is severely warped, time is flowing strangely, but locally everything seems almost normal. But you do notice something disturbing. The gravitational pull is stronger on your feet, which are closer to the black hole, than on your head. This difference in force stretches you out like taffy in a process physicists cheerfully call spaghettification. For small black holes, this would tear you apart before you even reached the event horizon. For supermassive black holes, you might survive crossing the horizon, but eventually, as you fall deeper, the tidal forces become infinite, and you're ripped into atoms, then subatomic particles, then who knows? Meanwhile, someone watching you from a safe distance would see something different. As you approach the event horizon, you appeared to slow down. Time dilation, a consequence of Einstein's relativity, causes time to flow more slowly in strong gravitational fields. To the outside observer, you never quite reach the event horizon. You just get slower and slower, redder and redder, as your light gets stretched to longer wavelengths until you fade from view, frozen forever at the edge of the black hole. Two perspectives, both correct, both describing the same event, but seeing completely different things. This is the weirdness of relativity. Inside the event horizon, things get even stranger. Space and time swap roles. Just as you can't help but move forward in time in normal space, inside a black hole, you can't help but move inward, toward the singularity at the center. It's not a place you're falling toward. It's a moment in your future that you can't avoid, like tomorrow. At the singularity, all the matter that fell in is compressed to infinite density. Space curves infinitely. Our equations break down. They start spitting out infinities and nonsense. This is where we reach the limits of our understanding, where general relativity and quantum mechanics collide, and neither theory can handle the situation. What really happens at the singularity? We don't know. We can't know, because information can't escape from inside a black hole. It's the ultimate cosmic censor, hiding its secrets behind an impassable barrier. For a long time, black holes were theoretical, objects that might exist, but had never been directly observed. We saw their effects, stars orbiting around invisible massive objects, jets of radiation being shot out from galactic centers, but we'd never seen a black hole itself. That changed in 2019. An international collaboration called the Event Horizon Telescope, actually a network of radio telescopes spread across Earth, working together to create a telescope effectively the size of the planet, captured an image of the supermassive black hole at the center of the galaxy M87. The image shows exactly what theory predicted: a bright ring of radiation from hot gas swirling around a dark shadow. The shadow is the black hole, or rather, the absence of the black hole, the region from which no light can escape, silhouetted against the glowing gas around it. This object is 6.5 billion times the mass of the Sun. The event horizon is about 20 billion miles across, roughly 3 times the size of Neptune's orbit, and it's 55 million light-years away. which means the light in that image has been traveling through space since before humans existed. When I first saw that image, I cried. I'm not ashamed to admit it. Here was an object that Einstein thought couldn't exist, that seemed too strange to be real, captured in a photograph. Here was visual proof that the universe is even weirder and more wonderful than we imagined. And now we know. There's probably a supermassive black hole at the center of every large galaxy. The Milky Way has one, Sagittarius A star, about 4 million times the mass of the Sun. We've watched stars orbiting around it, traced their paths, confirmed that there's something incredibly massive and invisible there. These black holes might have played a crucial role in galaxy formation. They might be the seeds around which galaxies grew. They might be connected to mysterious objects called wormholes, potentially allowing shortcuts through space-time, though probably not in any way useful for travel. They definitely break our understanding of physics in profound ways. Black holes remind us that the universe is not obligated to make sense to us. It doesn't care about our intuitions or our comfort. It just is what it is, and we're trying to understand it with our limited brains and limited senses and limited lifespans. And yet, we can understand some of it. We can predict black holes with mathematics, detect them with telescopes, image them with coordinated observations. We can probe the universe's strangest phenomena and come away with knowledge, with understanding, with wonder. That's the miracle, really. Not that black holes exist, but that we, fragile collections of atoms living on a small rock lasting for barely a century, can figure out that they exist, can understand something about how they work, can capture their image and say, yes, this is real, this is part of our universe, this is something we now know.